1 saat diye planlamıştım. Herhalde o yüzden yarısını, yani 10 dakika geçtiğine göre herhalde yarım saatini falan sunuma ayırıp 20-25 dakikasını belki soru cevap mı yapalım, yoksa soru cevap hiç mi olmayacak? Ona göre plan yapayım.
Soru cevap olur hocam en son, ama çok fazla vakit ayırmaya gerek yok sanırım. Hani normal sunumunuzu yapabilirsiniz bizim açımızdan sonra.
Çok soru cevap gelmiyor.
Başlayabiliriz. Şu an YouTube'da online.
Dear participants, we welcome all of you. Today we will organize our second workshop in the scope of BUCA IMSEF, International Music, Science, Energy and Engineering Fair 2021. Dear Tansu Daylan is one keynote speaker with the topic of the hunt for the extrasolar planets. We would like to talk about his brief resume. Astrophysicist. Dr. Tansu Daylan has graduated from METRO with a double major in electrical and electronics engineering and physics. Dr. Tansu Daylan is a transiting exoplanet survey satellite. It means TESS, postdoctoral associate with MIT with a visiting appointment at Princeton University. Before his postdoc, he was a PhD student at Harvard working construction novel statistical methods research for signatures of dark matter. He works on the discovery and characterization of planets beyond matter, beyond our solar systems, and detection of dark matter. Where he built novel inference tools using Bayesian statistics and machine learning. He is in a group of which is letting the lead of NASA's transiting exoplanet survey satellite and work on many aspects of the analysis of test data. The resulting test object of interest constitute a legacy catalog of exoplanet candidates likely to be transiting nearby stars and amenable to detailed characterizations of the decades to come. Dear guests, we would like to invite Dr. Tansu Daylan for his speech. You may take over.
Thank you very much for the kind introduction. I'll go ahead and share screen quickly, then we can get started. So today we'll be talking about extrasolar planets, also known as exoplanets. And I'll be giving a quick introduction to why we are interested in exoplanets and what we aspire to achieve, I guess, in the years to come, and what we have already achieved, kind of contextualize that, and then finish with basically a lookout for further progress in the field. So a quick definition, I guess, first is what's an exoplanet. And an exoplanet, or a planet beyond our solar system, is essentially any planet that exists our solar system that includes rogue planets as well as planets that are hosted by other stars. Now you may wonder what a planet is in the first place, and that's definitely a valid question. The International Astronomical Union already has an answer to that. In exoplanet field, we don't necessarily have the observational power to distinguish between different types or subtypes of planets. When it comes to solar system, we have very refined definition of what a planet is. It has to be, first of all, orbiting the sun, which is certainly not a criterion for exoplanets. Then it has to be, I guess, spherical. That's something we cannot know for exoplanets. That's an assumption we have. And then there's the criterion for clearing its orbit. Again, that's something we cannot check, but that's something that we are looking forward to doing so in exoplanet research in the years to come. So as you can see, we are basing the definition of exoplanets on the definition of a planet, but we are extrapolating that definition to regions of the universe outside our solar system. And next, I'll be quickly giving a historical introduction as to why exoplanets only came to be known in the last, I would say, maybe 30 years or so. Although in the astronomical community, there was a lot of interest in exoplanets throughout the 20th century. In fact, there had been many attempts to actually achieve the first discovery of an exoplanet. Unfortunately, they turned out to be either unconfirmed actual detections, or I'd say maybe people who suspected that some of the evidence could really point to actual exoplanets. Some of these turned out to be just wrong association, and some of them just turned out to be statistical fluctuations. But eventually, by 1990s, we had a good methodology shown to work to discover and catalog exoplanets. But going back ages ago, in fact, to ancient astronomy, our first cosmological model was basically an Earth-centric one, where we imagined the sky to be made of layers, each layer containing a different celestial object that moved across the sky, as at least as in relation to the fixed, otherwise what were thought to be fixed stars. So those 7 objects, including the moon and the sun, were the 5 planets that we could know or measure and show to be moving across the sky in ancient times. These were Mercury, Venus, Mars, Jupiter, and Saturn. And then through a lot of experimentation and interrogation, we came and arrived at the heliocentric model, thanks to Copernicus' work and others. And eventually what grew out of this was including a couple of other detections like Uranus and Neptune in the following centuries. In fact, if you want to also include Pluto, the 20th century, 1930s detection, which then, based on the IAU definition that I just quoted, was eventually excluded from the definition of the planet. That's a long story we can come to maybe at the end. But basically, we arrived at these 8 planets around the sun that pass the definition of what a planet is. Now, looking at these 8, it's very natural to think that there must be exoplanets, that is, planets just like our 8, but just orbiting other stars. When we look at this night sky, we see about 6,000, well, over the full sky, I guess, not at a given time, but about 6,000 naked eye stars. And if you just include the many millions and even billions of stars that are too faint for the human eye, you can imagine that, well, currently we extrapolate that number to be about 400 billion stars just in our galaxies. Think about that. Like if you had 8 planets just in around all the stars, that would mean a lot of exoplanets, in fact. Currently, we don't think necessarily that's that high, but we think that solar type stars have at least 0.6 or 0.7 planets per star around them. And the occurrence rate studies of even smaller, lower mass stars indicate that the number of planets per star must be at least 2 to 3 around M dwarfs or K dwarfs, so like smaller, lower mass stars. That means we do have a pretty big budget of exoplanets. And then it really takes an ambitious exoplanet research program to discover those and then characterize them. The nice thing is that we have a growing array of technological advancements and probes that allow us to extract a lot of information from these planetary systems beyond our solar system. I will mention some of them in today's talk. And as an output of all of this, there's an increasing interest in exoplanets, and an increasing fraction of the budget in astrophysics is being channeled into exoplanets because of this discovery potential, and how this discovery potential relates to our own origins, the origins of the Earth, the origins of our species on this planet, and as it relates to our broader definition of what our origins is, both from a planetary perspective and also from an astrobiological perspective. And very recently, as you probably already know, the exoplanets research got a Nobel Prize in 2019. Okay, so I guess I partly already motivated why we're excited about exoplanets, but just to lay this out more concretely, there are two main motivations to understanding or investigating exoplanets. One is to understand the origins of our solar system and the Earth in a way, in some sense, contextualize their origins in the much bigger picture of planetary formation and evolution in the universe. Because just looking at the 8 planets and trying to trace back their history into their origins is impossible because of all the stochasticity in this process. It's impossible to just look at one realization of a planetary system and deduce all its history. We have to be able to look at many different realizations of this stochastic process and then try to build essentially a model, a population model of how planets form and evolve. And while doing so, there are other processes like they generate atmospheres, they lose their atmospheres, they migrate within their solar systems, they get ejected out of their solar systems, etc. There are other secondary processes, all included in the definition of evolution. But then there's the aspect of just, I'd say, much more publicized aspect of just finding Earth's twin, or sometimes we like to say cousin, not necessarily twin, but just like a broader, more inclusive term that can include slightly smaller and slightly larger, or slightly hotter and slightly colder versions of our Earth, which we know to be in the habitable zone and to be actually habitable. And we would like to find essentially first the second instance and then more instances of Earth's cousins. Now, you may ask why? Well, for the same reason that we want to be able to contextualize life itself. We want to be able to say that we have a population model of astrobiology by sampling Earth cousins and then looking at their biosignatures and potentially even technosignatures to be able to say, okay, there are other planets and they potentially have this or that biosignatures. Now, first of all, does that mean that there's life? And if so, can we use this knowledge to look for life across the whole universe? Or does that tell us anything about our own origin, whether we have common origin with any other life that we may eventually find on any other exoplanet that may also reveal our own history too. Okay, so I've talked about the 1990s discoveries a bit while ago. Let me just take it back to that era. So in 1992, there was the very first detection of an exoplanet, or actually exoplanets. But those exoplanets weren't really found around sun-like stars. That was a pulsar, in fact, a neutron star with a misaligned rotation and electromagnetic axes, which means that it's radiating pulsations and radio waves, and you can actually detect those pulsations, measure their timing very precisely, and this very precise measurement then allows you to look for anomalies. And some of these anomalies are encapsulated in timing differences due to any orbiting object that causes the star to wobble, and this wobbling then causes a time delay, and then you can measure that to actually infer the existence of any massive object around a pulsar or any pulsing object. So that was done basically to first to find exoplanets, and then the 1995 detection followed around the Sun-like star, which then got the Nobel Prize. Now you may wonder, why are we even bothering to use these indirect methods, as I just described, this timing method, or as in the 1995 situation, that was the radial velocity method, which is essentially a very similar idea. You're not looking at timing of pulses, rather you're looking at, I guess, what appears to be a simpler method, which is you're looking for color changes as a function of time of a star. But these color changes are very small, so you have to do spectroscopy to resolve lines and then look for changes, I guess, in colors across time. And then using this methodology, people were able to find many more. In fact, starting in 1995 and moving forward, we have had almost 800, 900 RV detections by now. And by RV, I mean radial velocity. But you may wonder, like, why are we even bothering using these indirect methodologies? Well, it turns out, and I guess this shouldn't be a very surprising fact to you, that exoplanets are not very bright. And unfortunately, they are next to very bright objects called stars. So that is not a good combination. So you're looking for a very faint object next to and in the immediate vicinity of a very bright object. And just because of how optics work, this is a very hard task. In the very small subset of situations where this is at all possible, our detections of just actually resolving light from an exoplanet is constrained to those systems where the exoplanet happens to be young enough such that it has not lost its internal energy, so it's very hot. So nothing that we know of, like nothing that looks close to our solar system. So we are talking about very large exoplanets that tend to be very young and very hot, and also happen to be very far away from their stars. In such situations, we can actually detect directly the exoplanet. And obviously, this opens up a lot of different possibilities, because if you have direct light from exoplanet, then you can start studying its spectroscopy. Using spectroscopy, you can start studying, I guess, its composition, etc. And that also allows you to do biosignatures, technosignatures, etc. But the issue is, again, these are not exoplanets that we would have any hope of finding extraterrestrial intelligence or anything like that, just because these are very hot and very young systems. First of all, there wouldn't have been time enough to do any to undergo any evolution, biological evolution, because these are very young, and also they're just hot. So not very exciting from a Earth contextualization point of view, but certainly very interesting. Now, the exciting part is that our technology is advancing, and we just had the Astro Decadal Survey 2020, and there was a recommendation for directly imaging more Earth-like exoplanets, and some tens of them, some 25 of them, to create statistics. This obviously is a very exciting endeavor, and hopefully we will be able to talk about direct imaging of much smaller, more ordinary exoplanets in the decades to come. In a few decades, maybe 2040s, or maybe at worst 2050s. So that's certainly in the horizon, if not in the immediate future. So I've talked about radial velocity method so far. One thing I did not talk about is transit methods. In fact, that's the one closest to my heart, as I have been working on tests for a while. So I will kind of explain that now moving forward. But I guess I just had one slide on radial velocity. I've already described this, so I won't spend too much time on it. The idea is that you have basically a two-body system two massive bodies, one of which is bright. So you can infer the existence of the much fainter object, that is the exoplanet, by looking at the color shifts of the much brighter object, that's the star. That's the idea. Now, the transit method is a bit different. In the transit method, you're not looking at color changes, you're just looking at white light, or I don't necessarily mean white, I just mean broad passband, like it could be any light. You could be doing the transit search in red, in infrared, far infrared, whatever. And in fact, the transit depth can actually change as you shift your passband because of various reasons. The exoplanet might have a more, I guess, extended effective size in different wavelengths because of the constituents of its atmosphere, or sometimes when the exoplanet, I guess, has an escaping atmosphere, that might also be the case. But basically, the idea is the exoplanet is an opaque object. So when it transits in front of its star, because of the fact that it's opaque, it blocks some of the light from its host star. And because of the geometry, I mean, especially given that the exoplanet is very nearby, the solid angle that it subtends allows a appreciable fraction of the host star's light to be decreased or to be occulted. And as a result, we have a dimming as a function of time, which also happens to be repeating because you have a orbital plane and the orbital motion is periodic, or periodic to a very good approximation. So as a result, we have a periodic dimming of the host star if you wait long enough. Now, how long do you have to wait? Well, it kind of depends. Well, our typical orbital periods we have starts at like a small fraction of a day, like half a day or so, and then extends to many tens of days and sometimes years. With Kepler, the idea was to find long period planets, and we made good progress towards that. We did not necessarily achieve the design goal of finding Earths around suns, because that takes a very good photometric precision and also a very large baseline. Unfortunately, that wasn't achieved because of the various problems with the momentum wheels. With TESS, that's not really the design choice. With TESS, the orbital periods of interest are slightly shorter because of the slightly worse orbit photometric precision of the instrument. We have to phase fold many more times. We have to detect many more transits to actually achieve a slightly similar photometric precision. But basically, the idea is similar, that we need to phase fold lots of photometric data to find these exoplanets transit as they transit. Now, TESS looks like this. It's a spaceborne telescope. It's got 4 cameras. These cameras are wide-angle cameras. So you can actually see if I run the movie. These are very large cameras. Well, I guess, I mean, large is a relative term. These are these have apertures of order 10 centimeters. But they're 24 by 24 degree field of view. So as you can imagine, these are not very deep cameras. We only go down to, I'd say, 15th magnitude or so to do any useful photometry, although we can actually resolve, not spatially, but temporally resolve sources, photometrically resolve sources to much higher magnitudes. That's not really useful because our pixels are large, so we are very much confusion limited once you're past 15th magnitude or so. TESS, by the way, measures in the red bands. It has a single wide passband between 0.6 and 1 micron. And using its 4 large field of view cameras, it's able to cover a large fraction of the sky at a given time. This is a big advantage if you want to do a full sky survey, and that's what TESS does. In fact, it uses these 4 cameras to stare at a good fraction of the sky at a given time, and then it pivots about one of its cameras, camera 4, and then it pivots 13 times to cover a given hemisphere, and does the same for the other hemisphere, and then repeats. So far, TESS has finished its primary mission, where it has done this procedure that I just described. There was some interruption to this cycle in the northern ecliptic hemisphere because of the fact that the moon and the Earth come into view as you try to basically follow a schedule where you go anti-sun. So you basically take the sun just behind you and you stare at the patch of the sky that's away from the sun. But when you do that, sometimes the Earth and the moon can come very close, and as a result, we get scattered light from these very two bright objects. In fact, the Earth is very bright. If you're, I didn't mention that the TESS is in the Earth's orbit, but it's not in the low Earth orbit, as you could potentially guess. It's in a cislunar orbit, so it's in a 2-to-1 resonance with the moon. So it's very far from the Earth, but obviously it's Earth is a very, very bright object despite that. So we still want to avoid both the moon and the Earth, especially the latter, because it's large. So this is the orbit of the Earth, of the TESS, the Transiting Exoplanet Survey satellite. As you can see, it's in an elliptical orbit, and it's also inclined with respect to the orbital plane of the moon. This is again by construction. As it goes through perigee, as you just saw, it basically realigns itself to transmit the data that it has collected to the Earth. And we call one of these orbits, and concatenating two orbits into a data product, we call that a sector. A sector is about a month long worth of test data. And then using these sectors of test data, we can start doing analysis using obviously calibrated light years. We can do analysis for finding transiting exoplanets. One thing that you could imagine, one rule of this game is to have a long baseline, because we want to be able to look for signatures that may have, by these signatures, I mean transit durations that may be as long as a few hours. So the baseline is very critical. You want to be able to measure the photometry of a star for as long as you can. So that gives you essentially a baseline to do signal processing over. If you only, for example, measure with a baseline of a day or so, then finding transits become really hard. And as you can imagine, that is the case when you're doing ground-based transit follow-up or transit surveys, because, well, from the ground, you can only observe at night. So that gives you a baseline of a few hours. Then finding transits become really hard because you don't have a baseline. So it's hard to do relative photometry then. I've already talked about the fact that TESS has large wide field cameras. So this is how a TESS camera looks like on the sky, 24 by 24 degrees. And we have 4 of them. So in a given sector, they basically line up like this to eventually make a 24 by 96 degree field of view, which is pretty large. And it allows us to do a full sky mission. So currently TESS is in this first extended mission and is preparing to enter a second extended mission next year. With the first extended mission, we actually did something that we did not do in the first primary mission, or I should rather say the primary mission, which was the ecliptic plane. The ecliptic plane was avoided on purpose during the primary mission, but we are now covering the ecliptic plane in this cycle. So basically, as a result, TESS exposure map will have almost all of the sky, not quite the full sky, but almost all of the sky by now, which is going to be very cool. So this is again like how it was done in the primary mission. This is a video of the primary mission, but not quite, because as I said, in the northern hemisphere, there was a garage door that got open because of how the moon and the earth came into the field of view. So there was basically some departure from this uniformity. So overall, I think we covered about 75% of the sky, which is slightly short of the initial design. Okay, so the mission objective of TESS was to find small planets, but do it in a particular way, that is, find 50 small planets. And by small, I actually mean smaller than Neptune, and not necessarily measure their masses, but have their masses measured. There's a distinction between those two statements. TESS being a wide and single passband instrument, it cannot measure masses. In order to measure masses, you need a dynamical measurement, which is essentially a wobble measurement, which comes from radial velocities. And in order to do that, you need spectroscopy. So TESS can't do that. But the TESS mission was tasked with making this happen. So we had an extensive group of ground-based astronomers and facilities that contributed radial velocity data into a pool that's called the TFOP, or TESS follow-up program, which then enabled the mass measurement of these planets. And that basically allows us to start measuring their densities in addition to their radii, which we obtain from TESS data. So overall, TESS mission allows them to measure the densities of small planets, and that obviously opens up the possibility of finding and then characterizing Earth-like planets, and not necessarily just Earth-like. A good fraction of those planets are called Subneptunes, which are not necessarily Earth-like. They're, in fact, I'd say smaller cousins of Jupiter's, or maybe larger brothers or whatever, siblings of Earth's cousins. I guess it all depends on how you want to view, but basically the Subneptunes are exoplanets where we think that there's a large core, rocky core, but also an extended envelope of hydrogen or helium gas around this core. Now, why this hydrogen and helium gas couldn't reach the extent that is reached in Jupiter or Saturn, we don't know. Somehow the core accretion must have stopped because of inefficiencies involved. And it may just be that there was just not enough gas around when these planets actually formed. So for example, our Jupiter and Saturn, when they formed, they were able to accrete all of the gas around and they became giants essentially. Jupiter by itself, for example, contains almost all of the mass that is not contained in the sun, in the solar system. So that's somehow the core accretion was very efficient for them, but not for Subneptunes. So somehow they're an interesting population that we are trying to understand. But anyway, so Subneptunes, as well as super Earths, which are the more massive cousins of our planet Earth, they make up this population of what we call small planets. And TESS is a big investment and big game changer towards understanding, characterizing, and constructing a population model of these small exoplanets. So I think I have about 10 minutes left, given the transition to the next hour. I'd like to actually stop here and take any questions that may arise at this point, or by now, or will arise after this point. Yeah, let me just stop and take questions, because I also want this to be a bit more interactive. So any questions so far, or we can even conclude or make this the official conclusion of the presentation so that it actually triggers more questions.
We would like to thank those Dr. Tansu for his speech. And we continue with question and answer session. If you have any questions to our speaker, you can write on chat window or you can ask directly. This is your choice.
We can take your question, Asil Söyle and Bilal Esmer. First, Asil, please.
I want to ask question about the black holes. Are the black holes can merge?
Yes, black holes can merge, and they do. In fact, we have observational evidence that they do through the work of LIGO, Virgo, and the more recent gravitational astronomy telescopes that are coming online. We have now growing evidence that they do, and in fact they do so efficiently. That is, I mean, black holes are rare objects. So as a result, one could imagine thinking about this as a theoretical possibility, but not actually being realized in nature. But rather, it's that black holes are rare, but still they're finding a way to actually merge in a Hubble time and that we are able to observe them.
Thank you for informations.
Okay, thank you. Bilal Esmer, we can take your question.
Okay, what happens if the TESS encounters a solar flare?
Solar flare, I guess you're asking about the flare from our sun or from a different star?
Okay.
Okay, so I guess from our solar, all right, so as a nuisance, if we were to get a solar flare, I guess depending on the magnitude of that solar flare, if the solar flare was really strong, it could knock out all space-based electronics. That's possible. So that would certainly be bad news for TESS. It hasn't happened. But it's also that TESS is not directly looking at the sun, obviously. It would be way too bright for TESS. So optically, it's not an issue since we're not looking at our star. For other stars, we have capability of readily observing stellar flares from other stars, and that's a thing. In fact, we have surveys using the TESS data to find and characterize and catalog stellar flares, and the frequency of stellar flares tell us about the biological potential of the stellar system, because the more flares you have, the more opportunities you have for inducing biology or changing, I guess, in affecting, let me say, biological processes in the planetary system. But also at the same time, it's a stirrer. So basically, if you had any life that could arise potential or is in the process of arising, then it could also knock out the UV and X-ray radiation from the stellar flare could knock out the initial seed of life.
Thank you for answering my question.
Sure.
Thank you. Is there any question? Well, I have some question for you. I know you were as researcher at CERN for a while. And can you
Correct.
please share your experiences with us in the CERN?
Okay, so at CERN, I was an undergraduate researcher working on AMS, AMS-02. And I guess, let's see, I mean, during undergrad, I was into particle physics, which basically started to go away when I started PhD. Although my initial interest in particle physics eventually got me thinking about dark matter. but from an astrophysical point of view. So in some sense, it allowed me to broaden my interests to include dark matter, which then turned out to be my PhD topic. But it also, like I was there as a summer student first. So the summer program there, I got, for example, many friends with whom I still sometimes communicate. And we also, I remember, attended lectures that were very enlightening in some sense, especially with regards to courses that I had not taken at ODTÜ by then. So yeah, I think that was a very useful experience, although it was slightly decoupled from what I eventually ended up doing as a professional researcher.
Great, thank you so much. And then my second question is, what is your motivation to work about astrophysics? Why did you choose this area to work on it?
Well, astrophysics, I'd say, is, historically speaking, the observational side of it, astronomy, is the most fundamental science. So, I mean, as a baby or child, as we are born into this universe, the very first, typically the very first thing that excites us is the night sky, and that was certainly true for me too. I would basically, when we go out to our summer house, I remember I was just very excited to make small observations that eventually turned out to be like a almost like a worldview, to collect small features of the sky, and then obviously go ask people and try to do my own research on it. So I really liked how we could contextualize our own origins on the sky. So basically, obviously exoplanets back then wasn't really a thing, but when I was a child, the problem that really fed my imagination was dark matter. I mean, not from a professional point of view, but mostly from a very non-technical point of view. I guess one thing that I clearly remember was that when I was a student, the dark energy made headlines for the first time, in fact. Like I'm talking early 20s, sorry, early 2000s, I mean. So back then, dark energy was found to be a constituent of the universe. We had the WMAP results that come out, etc. So there was a lot of cosmology excitement, and I guess I was very much interested in being a part of it.
Okay, thank you so much. Is there any questions from our participants?
Yes.
Yeah, I think Bilal Esmer want to ask something.
How resistance is test to metal fatigue, and did you have any recommended for the young scientists?
Okay, so I think I got the second part of the question, recommendation for young scientists. I did not get the first part. Well, okay, I can address the second part at least. So I'd say for young generations, if you really want to be involved in research and/or astronomy and/or I guess physics, you need to think about research from as early as possible. So that's not something that I want, like I'm bringing up just because that's eventually going to be what you're doing. It doesn't have to be. You may eventually choose to go into academia or just do something completely unrelated. You can do whatever you want to do with your life. But eventually, the culture of research does give you problem-solving skills that will be useful throughout your life. So doing this early on, working on a particular problem, this could be as simple as just coding something to analyze some data set, or contributing to a design process, I guess, like experimental design, I mean. Any of these exercises will eventually help you become better scientists. And by early, I literally mean like high school and potentially early undergrads. And you can do this by either pairing up with other students, or just pairing up with a faculty from a university that if you have access to, or just through your connections of your high school teachers, I guess. Either way should work, but you should definitely do, you should take concrete steps towards achieving small but realistic goals in research if you want to be professional researchers. But as I said, this also has applications much, I mean, well beyond the research culture itself.
Thank you so much.
I would like to ask a question. We have seen two countries, maybe more, in academic life. How do they look in America, the philosophy of science? I think it's the basic motivation of scientific researchers. Can you compare here and there?
Yeah, so I would love to. The only thing is that I was a student in Turkey, and I'm more like a advisor. I have a more advisory and leadership role here. So when I try to make comparisons, that's a bias factor I have to kind of watch for. In Turkey, I really enjoy being a student in Turkey. That's because I was obviously in one of the top-notch institutes in Turkey. I really like ODTÜ. I think it is, I mean, if it wasn't in Turkey, if it was somewhere in the US, for example, it would definitely be one of the top universities in the world. Like, I think it really has a really good quality. The student population quality is really good. That's evidenced by the fact that its student population is able to find very good careers outside of Turkey very easily. It can achieve a lot. And the faculty themselves are typically educated, get their PhDs abroad, and then eventually come to Turkey as ambitious early career faculty. So they also want to achieve a lot. So I think that was a really nice combustible mixture, and definitely worked really fine. So I definitely think that's a great university, and that can also be generalized to a couple of other really good institutes in Turkey too. The issue is, I think, in the general academic culture in Turkey, which is that there's not much of an incentive to achieve a lot. If you go outside some of the, I guess, very restricted borders, there's really no motivation to make substantial contributions to science, because there's nothing to gain literally by doing so. Like, we don't have good funding, we don't have good prizes, we don't have a good academic culture, and these are all unfortunately problems with sustaining good people working in Turkey. I think that's a big problem. In the US, that's obviously the case. There's a lot of motivation for coming into US to achieve big things. But some of the things that I would be able to say for METU, for example, may not necessarily be true, like student population, because obviously US has a great student population too, but it's not like Turkey, where all the good students go to a couple of particular institutes. In the US, it's much more diverse. So it's not like you will get all the good students by going to a particular institute. It's not going to work that way. So it's more like a random sampling, I'd say. But I'd say that there's good motivation to achieve a lot and make good contributions to science in the US, and I think that's what I really like about it.
Thank you. And we have some questions on the chat. First one from Yıldıray Ateş. First of all, hello. What should we do to become an astrophysicist?
Okay, so as I said, research is one thing, and I'd say maybe the most important thing. Beyond that, you need to get a PhD. That might sound obvious, but you need to do that. And in order to do that, you need to get a good degree, a bachelor's degree from a good, I guess, college. So that means eventually you need to go up the academic ladder in a way that can be evidence of your leadership in however you want to define it. Sometimes this is defined definitely from a research perspective, but sometimes in other things, like you need to be multidimensional too. Research is an important thing, but you need to also add other things to your work environment. Like you need to be able to, you need to have good grades, you need to be active in the astro community, add, I guess, to the diversity or the culture in wherever you work. So those are also important, especially in the US. But again, I would say at the top of the list is always research, the papers that you lead, your leadership ability, your innovation, and these are all evidenced by basically the talks you give and I guess the papers you write, etc. And some of this, at the end of the day, may also have to do with whom you work. So you need to choose your institute very wisely, but more than the institute, the person that you work with.
Thank you again. The second question from Yiğit Kaan Kızlıer. What will happen if people find what dark matter is? Why is the dark matter important and what does it do in space?
It gravitates in space, I guess. I don't think it has purpose other than that, although we may eventually find otherwise. I mean, what will happen? Well, I mean, we would all be very happy, I guess. Solving such a big puzzle in astrophysics, even though it sounds exciting, is also a bit scary to me too, just because, I mean, without big questions, science is not as exciting. So I'm pretty sure that even if we found dark matter, like by that I mean get a signal that reveals its particle nature, eventually we will still want to explore further, because like it's really like peeling off layers of the onion. Like you need to, even though you understand something at face value, there's going to be levels of detail or levels of complication where you can ask further questions, and then those questions will remain unanswered. Will there be a time where we answer all the questions there's to be asked? That sounds like a very scary point, if it ever arrives, but I don't think it will arrive anytime soon.
Okay, thank you. And Yıldıray Ateş also thank you, teacher Tansu, for answering this question. He said that. Is there any question? You can ask directly or you can type on the chat. Yiğit Khan also thanks for you.
Sure.
YouTube'dan da Eren Alp'taki Nice Workshop demiş.
Yes, on the YouTube, Eren Alperen said that a nice workshop. Serap Kızlar said that thank you for the presentation. You are such a good role model. And yeah, we have one more question from Indonesia. What about the gravitational waves discovered in 2016? Can it still be researched?
Sure. Yeah, gravitational wave astronomy has a bright future. I'm sure people entering the field will want to think about gravitational wave astronomy as seriously as a potential subfield of astrophysics to pursue. I think there will be more funding reserved for it in the years to come as we move into this so-called multi-messenger era. That means we are able to observe the sky not just using photons, which are messenger particles of electromagnetic force, but also of other messengers like first the gravitational waves. Gravitational waves are not necessarily particles, but they're excitation modes of another fundamental force in nature, but also other particles like neutrinos. So we now have the ability to correlate these signals in time, and then that also allows us to find where they are coming from, which then allows us to understand the objects which emanate them. So overall, we are able to produce a much better picture using multi-messenger astronomy. So definitely, it is still researchable, and there will be many more candidates coming out in the decades to come.
Thank you so much.
If there is no more questions, that will be all.
Yeah, I think yes. I think that's all.
Yes. Dear participants, our workshop is over. We thank you, Tansu, Daylan. Thanks for your participation. That was a lovely speech.
Yeah, thank you
Thank you
so
all.
much again for your accepting our invitation and participating in this workshop. I think it's very useful and enjoyable for us.
Yes.
Thank you so much.
Thank you for your invitation, and hope to see you again.
Hope to see you again.
Nice to see you.
Bye.
All right, take care all. Bye.
Thank you. Thank you.